threshold, you can do more work, right? So the shock wave just cause a drop in the ability of the gas to do work. Makes sense? So when you, anytime in the future, anyone asks you pressure loss, it's always about stagnation pressure. Now in this case, of course, it's because of shock wave. And the shock wave is a highly non-isentropic process because S2 over S1 or S2 minus S1 will be very large. The larger this is, the more negative it is in this bracket. That means the smaller the exponential function is. So that means the smaller this over there, right? So it's pretty bad, you know, pretty bad. The entropy increase really cause the stagnation pressure to lose exponential. Right? So you certainly want to avoid. And this is even more important under high Mach numbers, right? Because the higher the Mach number is, the decrease in the Mach number is stronger. Your S2 over S1 is actually larger, or S2 minus S1 increase, right? And even if the entropy increases just linearly, your stagnation pressure loss will be exponential. Right? So you would like to try to avoid shock waves. Questions? Now let's have an example.
So claro, no.
You were thinking of quiz. I lost the word. So let's pretty safe now. By the time we finish this, we don't have time.
Yeah, you gotta run that back, bro.
Now, say this is your reservoir, PR is equal to 1.0 megapascal, which is of course 1,000 kilopascal, right? PR in reservoir is equal to 800K. But R also means, since it's in reservoir, so it's not moving. So any pressure and temperature in there is also your stagnation pressure and stagnation temperature, right? So if you have an isentropic process, these values are not going to change. What will change is the static P2 or P1 and T1 and T2, right? But if it's an isentropic process, PT will not change, and then PT will be this. And TT will also not change, right? But TT is more interesting, even across the shock wave, it doesn't change, right? Because shock wave is so thin, there is really no mechanism for heat transfer. Right? Not just because it's so thin, it's also so fast, right? No time for heat transfer either, right? So here the question is that your A exit over A throw is given as 2. So here's your A throw. Here's your A exit. Cross-sectional area is 2. What is your question now? If there is a standing normal shock wave at exit, PB is equal to what? Let's revisit this issue. This is such a good example. Okay? Someone borrow a piece of paper to illustrate the shockwave and the conversion diverging output. There's this one, right? And there's a conversion diverging also. I couldn't find it anymore.
Oh, give me your notes.
Okay, no problem. I will draw it again. If there is a standing normal shockwave, let's say. So let's call this location right upstream is 1, right downstream is 2. Right? So your PB really is equal to P2, right? Because right downstream of the normal shockwave, the flow becomes subsonic. So that means it already adjusts to ambient pressure. Right? So this condition you should be able to agree upon.
Yeah.
Does this sound okay? Anyway, you think about it even a step removed further. The flow is adjusting to the ambient pressure through a shockwave. That means upstream of it must be supersonic, downstream of it is subsonic. That's how it adjusts to the ambient pressure. So P2 has to be equal to PB. But this also means M1 is greater than 1. Also means that otherwise there's no way for you to have shockwave. If M1 is greater than 1, that means M at the throw is equal to 1. Right? It has to. Right? So by now you have to know all this now, right? If you have thought about this, you need to catch up a little bit, okay? Or come and ask me, I will explain to you again why this is the case. Okay, or ask some of your classmates. So that means your ATH is also equal to A star. Right? So AE over A star is equal to AE over ATH. The reason you wrote this, you don't need to write that, but if you can write this, that means you know MTH is equal to 1. This is equal to 2. That means M1 is equal to 2.20. How do I know? When you look at paper, right? Now, I'm going to follow your proof message. Page 632. This is for gamma 1.4. Or here, you need to say gamma 1.4. It's called a purpose. In air. It could be just nitrogen. Okay? So, if your Mach number is equal to 2, your downstream Mach number is equal to 0.5774, and you have all these numbers here. The ratios that we have, just divide. They are simply calculated. So, P2 over P1 is equal to 5.480. But to know P2, meaning to find PP, you need to find P1. So what is P1? P1 over PT1 is equal to 0.09352. This is isentropic, right? Because when you are talking about condition 1, there is no shock wave yet. So it's isentropic, or you assume it's isentropic, otherwise we don't know how to solve it. So 0.09, okay? So your PP equal to P2 is equal to P2 over P1 times P1 over PP1 times PT1, right? You see this in your textbook all the time. This times that, times that, times that. That's really nice, right? That means you figure it all out. So this is equal to what? 5.480 times 0.09352 times 500 kilopascal. This is equal to this is 1,000 kilopascal, right? So this is equal to 512 kilopascal. I'm already some decimal places. So that means your back pressure really is 500 joule. So what this says is that, remember, we have this P over rotation here. That is this condition. That is that condition. Because if your back pressure is here, you will have fully expanded valve, right? Perfectly expanded. And if your back pressure here, it will cause a shock wave here. If your back pressure is here, it will cause a shock wave. And if your back pressure you keep increasing, the shock wave keeps moving upstream. And by the time your back pressure is here, your shock wave really is a trivial shock wave, meaning it's right at the floor. It goes from M1 equal to 1 to M2 equal to 1. You have to think about it. But then the pressure is a little bit above that, so it becomes a subsonic all the way through the diverging section of it. Right? But for this particular example, that's what you have. Now, so additionally, because M1 is equal to 2.20, so your PT2 over PT1 0.6281. So pressure loss is equal to 0.6281 minus 1 times 1 megapascal. So that's 372, about 372. You have lost that much. We have lost that much, right? Okay, and this is really your problem 8 in your textbook. I think it's a good problem to work on.
I didn't get that.
Now, later on, we would also deal with what happens if shock wave is there. So, if shock wave is somewhere within the diverging section of the laser corresponding back pressure, right? Or you would say that I know a back pressure, find where the shock wave is. Okay, and that's not so trivial because the shock wave being at the exit is kind of easy, right? That's kind of like a limited condition. You already said it right there. Now, what happens if I said, hey, if my back pressure is, let's say, 700 kilopascal, what would be the shock wave? where will be the shock wave? Huh? Now, for that purpose, we have to deal with another issue. Because the flow is not isentropic, then what will happen? Now, if I imagine this is the question. Like, where is Collins and Diego, right? So, gotta do this. If they say this part is very important, or just about everything we have in this class is important. But this one will give you a very powerful tool to handle where the shock wave will be. Right? Let's say if you have a shock wave somewhere here, and let's call condition upstream 1, immediately downstream 2. This is, let's say, this is the inlet to your channel, and this is the exit to this channel. If somewhere you have such a channel. And of course, when we talk about shock wave, we are talking about supersonic flow, right? So clearly M1 has to be greater than 1 and M2 has to be less than 1. But if I just give you a piece of duct that is diverging like this, and supersonic flow at the inlet, let's say Mi greater than 1. So you know M1 is greater than 1, and M2 is less than 1. So your ME will be also less than 1. This is what you can already say, right? Because after shock wave, the flow becomes subsonic. That means M2 is less than 1. And now M2 is less than 1 means what? It's going through a diverging section of it. It would become even more subsonic, meaning ME would be even greater than, even smaller than M2, right? But M1 is greater than Mi, because your Mi has to be supersonic. Simply because if you want your M1 to be supersonic, and that's acceleration, so here M1 has to be Mi has to be greater than 1. It cannot be less than 1. Because if Mi is less than 1, it cannot accelerate in the diverging section of it, right? So once you think about it, once you can label all this, you have some achievements, right? You just say, oh, okay. If you want to label it like that, fine, I will accept it. Don't do that, okay? Even when I said it's true, you say, oh, Dr. Chen, you say so, yeah, I agree with you. Most of what you say in class I believe anyway, so I might well just believe this. But you cannot, because if you are given a new problem, you have to reason this out, right? Okay, so what this says is, again, very nicely fit with the idea that we had earlier. Even if you cannot see Cocoa Beach from here, you know that there is a sea level out there. Then we call it AI star, meaning what? There is something that you can refer to there where Mach number is equal to 1. And the reason I call it AI star here is, and the reason I call it AI star is that's a reference throat area for your inlet condition, right? If I know what number at the inlet and I know the cross-sectional area, I should know the cross-sectional area of this throat. Make sense? Because it's all isentropic, right? Now, what happened after shock wave is this. Your PT2 is less than PT1, right? So this is important. Think about your M dot is equal to PT1 AI star square root of RTT square root of gamma plus 1 over 2 gamma plus 1 over 2 1 minus gamma, right? Am I correct on that? equal to steady flow. PT2 RTT. You can say TT1 equal, but TT1 equal to TT2, there we go, right? So here's A. You can imagine there's such a thing. So here you will have your A, E star, square of gamma, plus 1, 2, gamma plus 1, over 2, 1 minus delta. See, because R, well, unless you have a chemical reaction, but let's assume there is no chemical reaction, the composition does not change. So R remains the same. If you want, you can say R1, R1, gamma 1, gamma 1, R2, gamma 2, gamma 2, right? But R1 equal to R2, gamma 1 equal to gamma 2, without chemical reaction. Then, because PT2 is, so that means what? PT1 AI star equal to PT2 AE star. So AE star over AI star equal to PT1 over PT2. This is going to be a very useful concept later when we are trying to find out where the shock wave will be. So, what you are thinking here is after shock wave, you say, well, after the shock wave, if I want to accelerate the flow to be sonic again, what would be your throw area? So your throw area now has to be larger than the throw area upstream, right? Remember, in isentropic flow, that throw area is the reference area, right? Which is true for the flow that is isentropic. Now, in this case, isentropic flow is this upstream of the shock wave. It's also an isentropic flow downstream of the shock wave. However, there is a line there, or there's a surface there that says that these are two different thermodynamic states. So they would have different reference flow areas. Make sense? Remember your isentropic relationship P2 over P1, T2 over T1, P2, or isentropic P2 equal to PT1, so on. But your P2 over P1 or P over PT, those are all in the same table as A over A star, right? It's in the line, meaning that these are all related. All right, but after the shock wave, these are also all related. The only exception is what? PT2 is not the same as PT1 anymore, and AI star and AE star are not the same anymore. Right. So, if I want you to find out a Mach number at any location here, you don't refer to this area anymore. If I know this cross-sectional area, I should refer to that. And even that is not existent, you would have calculated it. Make sense? Yes.
I didn't quite understand. What does AE star represent?
AE star is if you want to accelerate the flow to be sonic again. That's the throw area you should have.
Does AE star only increase in area because of the shock wave?
Mm-hmm. It can only increase because PT2 is less than PT1. So see, you have the shock wave. What does that mean? This is when it just knocks all your references are. You change the reference, right? You were so disoriented. Now you think east is west, west is east. Well, this is not that bad. It's just numbers. Shockwave basically just disrupt everything. So changing your references, right?
So then ME star is 1, theoretically.
No. And E is here, right?
No, like if there was a theoretical ME star, it would be 1.
At the new throat we made.
Yeah, that's right. Anything with a star is not is equal to 1, right? No. By definition, yeah. So now, let's say, let's go back to that example. This room is cold, isn't it? Pretty cold, right? You're all sitting there, not even moving, it's cold. My weak point is here, when the cold air comes down, I touch it. Anyway. So now here's the issue now, right? If you imagine this is connected to a reservoir, and you have the acceleration out here, and I said, hey, if shock wave is here, what is the Mach number? Ah, right? So you said, okay, if shock wave is here, and I know, if I know that, which you will be able to calculate, or you simply just know, you say, okay, if shock wave is this at such a location, then I know MT. And I can calculate AE, because I can calculate AE star like this. And then I find this and refer to that. I know the Mach number, and I know everything. Right? Okay, now, if you would give me a couple of minutes more, maybe we can finish one more example that would that will be better, okay? Because then you have something more to think about. Now, this is really in your textbook. Example 4.3 is on page 126. I think it's the very first on 1.2. So what you have is, you will have this. Here is your AI, and you will have a shock wave at a location. Let's say this is 1, this is 2. Your A1 over AI is equal to 2. But your MI here is equal to 2.0. PI equal to 100 kilopascal. TI equal to 270 Kelvin. And your AE here, AE over AI is equal to 3. PP is equal to 1. Or you can say, I can reverse this program. By the time I know PP, I said, if that is PP, where is the shock wave? Right? So what you would do here, look, because your MI is equal to 2.0, so your AI over AI star, imagine you have that, right? Will be equal to 1.688. So your A1 over AI star, because I want to find out the Mach number here, and then I can find out the Mach number downstream, and then I can find that, right? Is equal to A1 over AI over A star. So this is equal to what? 3.376. So this gives you M1 equal to 2.762. Table. Okay. So, and then M2 will be equal to 0.49. Okay, table, right? This is isentropic table. This is shock table, right? Then your AI star over AE star is equal to PT1 over PT2, and PT2 over PT1 is equal to 0.4021. Or you can say AE star over AI star is roughly equal to 2.5. Okay. Now, then your AE over AE star is equal to AE over AI, AI over AI star, AI star over AE star. Right? So AE over AI is equal to 3. AI over AI star, much earlier we should have found it. I'm sorry. Oh, here, 1.688. AI star over AE star is equal to that, 0.4021. So this will keep your value is equal to 2.04. So that means your ME is equal to 0.30. So how do you find out? Your PB will be equal to PE in the flow. So it's PE over PT2, PT2 over PT1, right? PT1 over PI. So this is, are you following this? I'm probably going a little bit fast, but let me do it now. At least you can think about it, and we will come back and finish it. This PE over PT2, because downstream of the shock wave, you assume it's isentropic. So this is the isentropic table. PT2 over PT1, this is shock table. PT1 over PT is isentropic table again, right? Because here your ME is equal to 0.3. Here your MI is equal to 2.0, so you can find that. Here your M1 is equal to 2.762. So you look up the table for these three conditions, and then you times the PI again, right? Because you know the PI is 100 kilopascal. So you will find out this is 295.6 kilopascal.
Yeah, okay.
Is that all of it times PI?
Times PI. Because eventually you will have a pressure, right? These are all just the ratio, and that gives you the uniform pressure. So
we did.
Come back first and we will revisit this again, but at least now you got something to think about. Okay?
How you do? See you
Come
later.
back with questions. Think about it and come back with questions. Okay?